Hello, and welcome to Tech Connects, Dice's podcast where we dig into the topics on tech hiring, recruiting, and careers that matter to you. I'm your host, Nick Kolakowski. Our next guest on Tech Connects is Christopher Savoie, who's the CEO of Zapata AI, which is figuring out how to best integrate artificial intelligence into industrial scale applications. In other words, he spends all day thinking about how to make the massive systems that underlie our lives, from supply chains to manufacturing hubs, even smarter and more efficient. If his name is familiar, it's because he's the co-inventor of AAOSA, the AI-based natural language interface technology used to develop Apple's Siri. So he's been in the AI game for a long time. I wanted to get Christopher's take on the future of AI, the risks we need to be aware of, and the complexities of deploying this technology at enormous scale. It was a fascinating conversation and moved very quickly with a ton of points covered, so buckle up. I wanted to start out, for those who are unaware and who are listening in, what exactly is Zapata AI? I mean, I know that coming into this call, I was talking to some people about how you're dealing with enterprise-grade AI and so on, but I just want to kind of dig down into that for those who don't know.
So thank you for having me, Nick. The company, I guess, talking about the background of the company, we came out of actually a theoretical chemistry lab at Harvard that does quantum algorithms. So really advanced linear algebra, super propeller head math, right? Applied to some of the hardest problems in the universe, quite literally, like particle physics, quantum chemistry. These really hard quantum math problems, which are just like super hard, super high dimensional math problems. Like, this electron is, in my fingernail, but it's also on the other side of Andromeda, and it correlates with a quantum correlation with this other electron, blah, 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 in this molecule. So how does that affect how it's going to bind to another molecule? That kind of stuff. So that's important in drug discovery. It's important in, particle physics, these really, really hard, super propeller head problems. So we came out of that math background. We're like, where are we going to apply this to, right? And we wanted to apply it to, from the very get-go, to some of the hardest industrial problems, because that's where the big math problems are, right? In industry. But those things tend to be, high-value business problems. Things like, how do I optimize a supply chain? That's a really hard math problem, it turns out. When you have 10 nodes or 20 nodes of places to travel in a logistics thing, that's not a problem. You get up to thousands or global supply chain, it becomes mathematically intractable for a lot of algorithms. So we had this really cool high-end math, and we had the ability to apply it to these kind of industrial problems that are really, really hard, but they're worth a lot of money, billions of dollars in the world.
So the interesting thing that immediately jumps to mind for me is that, as you mentioned, the sheer computational complexity, once you start introducing all these different variables, is immense. It's mind-blowing. It's literally server melting, depending on what servers or data centers you're trying to process it in. Given sort of just like the sheer scale that we're talking here, it sounds almost too complex for anything short of a quantum system to really be able to handle. So how did you even begin to approach something this size? I mean, I know there's like kind of small bites of the elephant, but I mean, what were those initial small bites? How do you scale up to something this size, given how complex it is?
In a way, it's actually the opposite mathematically. We're trying to scale the problem down. We're trying to simplify, and we've become really good at doing that, even without quantum hardware. Eventually, we'll have quantum hardware, which is really the dream. That's the holy grail. When we can run this linear algebra natively on natively quantum things, we're going to be able to do that exponentially quicker. But the good news is we've been able to learn how to do quantum chemistry. We've been able to learn how to do quantum physics on supercomputers, on GPUs, pretty efficiently now. So we can't do the exact calculations brute force, but we've learned a lot over these decades about how to do that linear algebra using things that, the technical name is tensor products, tensor math, tensor networks instead of neural networks, which are just much more efficient at processing these large latent spaces, these large dimensional problems. So we know how to do this even without the quantum hardware much better than we can do it using, say, neural networks and the kind of things that, say, OpenAI runs on today. So we've kind of advanced the math. It's not quite to the point where we can run it on quantum hardware because the quantum hardware is not there yet. But we can still do a much better job with the same quantum math on GPUs today than using typical math. Does that make sense?
No, it absolutely does. I guess, I mean, the other question I have related to this is, and I'm obviously I have a very beginner's perspective on this, but when I think about industry, I think about processes that are iterated over decades, but haven't really taken a super leap forward, that things kind of, iterated and streamlined and so on. And also that they're very set. I mean, it's not, the methodologies have to be done a certain way because you're trying to produce a certain product at a certain time in order to ship it in a certain direction and have it get there at a certain, within a certain time frame. How do you integrate AI and sort of even just this mathematical thinking into these old processes? I mean, is it an enormously kind of difficult endeavor to get clients to kind of absorb this way of thinking? Has it been easy? I'm just trying to wrap my head around it a little bit.
I think it's somewhere in between, right? We can use generative modeling using these quantum statistics to do a really good job at being better at understanding what these humans are doing in their minds, because a lot of these processes are still manual. You might think that that FedEx has this super algorithm that says, okay, what box is going to go on what pallet into what truck into what boat and blah 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 around the world. No, that's actually not how it works. It's very much localized. There is some processing of, okay, which ship is going to go where. There is some scheduling and planning. There are systems that do that. But when it comes down to it, it's a person, right? A man or woman with a clipboard and a piece of paper saying, yeah, I think we can fit one more pallet on that truck.
Yeah.
And it really literally is that. And, it has to be handled locally because the computation to actually do that with a computing system to get it super optimized is too hard. And so a lot of these processes haven't been. So that's one problem. We can do a really good job of actually automating those processes. And generative modeling allows us to take what's in the mind of that human and kind of adapt it, kind of digital twin it by learning the distribution of following the data of what is a good pallet loading and what is a bad pallet loading. Just like we can learn to deep fake what does a cat look like and make a cat that doesn't exist, we can make a better pallet fitting algorithm, right? Using generative modeling, which is pretty cool. So we can actually take that knowledge of the human in one of these processes out of the loop in a sense by imitating what they're doing. That's the cool thing about being generative. We can do that kind of human-like thing of being creative, right? Understanding the distribution of good solutions and then sampling off of that distribution. That's how we deepfake. But we can deepfake more than just fake pictures of cats. We can deepfake good solutions for putting pallets onto boats, for example, right? So that part's easy. The harder part is getting the humans to trust the solution, right? That really is, a process over time. Like with Andretti Global, we the first year was about, okay, how do we get that knowledge? How do you predict like a yellow flag? What are the things that go into there? What are those constraints? What are the people thinking about on the track? What variables really don't matter? And what does the historical data say about that? So building the initial models was 1 year of process. The second year was bringing it to the track and kind of testing it. Does this work? Does it not work? The third year, and this has been the hardest thing, is okay, how do we make an application that fits into the way that humans work and think, right? It's one thing to say, oh, you need to shove one more pallet onto that truck, but getting the human to actually put that into their workflow, put that into their thinking and say, you know what, I need to trust this computer. I can fit another one in there. I'm going to do that, even though it might contradict what my intuition might be for this particular instance. That part's harder. This is change management. It's the same time we've introduced any computer system, like, oh, point of sale system. I just want to use my old cash register, a calculator. No, I want to use my slide rule. Every time we have technological change, there is this human element of learning to trust it. A lot of people didn't want to, in baseball, the sport of baseball, trust the shift or trust that, statistically well, it doesn't make any sense to leave a gap between third base and second base completely open. That makes no sense. Somebody's going to just hit it there. But the truth is, statistically, they won't over a season. And the
Yeah.
shift worked. It worked so well that they've made it illegal now. But getting people to trust it initially when it was working was a hard thing to do, right? Because it may be counterintuitive. So I think the answer is somewhere in the middle. Can we create a system that's better? Yes. Can we replace some of the human inputs into these systems that are kind of subjective? Yes, we can use a kind of subjective statistical system to do that. Can we get the human to actually accept that and want that and integrate it into their workflow? That's the harder part, and that takes time, and it takes planning, and it takes change management.
I imagine that, like any technology, it's also a matter of sort of a learning curve or a comfortability curve, for want of a better term, where, once they see it in action, once they realize that, yes, this system is helpful, then you start to see hopefully accelerating adoption on that front. Is it one of those things, too, where, I mean, a lot of what we're seeing with generative AI across industries is prompt based, where they expect the user to sit in front of a terminal or on their phone or whatever and ask it, a particular question, and then receive an answer. And I assume, I mean, is that sort of the same from an end user perspective? Is that sort of the same model that you're envisioning here? They have, to go to the UPS example again, tons of workers out there with whatever their terminal of choice is, saying like, how do I fit the pallet? Or is it something that's more on kind of a manager level? I mean, how is it? Because these systems are so huge. I mean, how do you make the end user aspect of it the most efficient possible?
Well, I think the first clarification that we should make, there's been an amalgamation, I think, due to the success of ChatGPT, that generative AI is chatbots. It is natural language as an interface first, right? It is DALL-E, where you type, "I want to see a purple polka dotted cat with no tail,"
Yeah.
and you get that.
Yeah.
So natural language has been kind of amalgamated in people's minds as that's what generative AI is. Generative AI equals LLM, large language model, equals using language, and the output is language, and the input is language. But a lot of the problems that we see in industry, they're not really language problems; they're number problems, right? And so it's not clear that the best interface for knowing when there's going to be a yellow flag in racing is there might be a 50% chance of yellow flag and having to read that. It's actually better to give a visual of a graph that, hey, the this has been augmented to above 50% chance, and have it kind of as like a heat map, right? Or a dial, or something that's more visual. That may be the better interface. And then the inputs to that tend to be numbers, right? Yes, you could ask it a question or do a prompt, but sometimes it's just it's the numbers inputting into a system, giving you that prompt, right? For lack of a better term. So you really don't need the natural language interface on the front end either. That may be very inefficient to sit there and type, "Hey, what is the average lap time going to be for car number 26 for the next 5 laps?" No, that should just show up as a graph. So the UI aspects of generative modeling, I think, in people's minds have been kind of force fed and pigeonholed into natural language, because that's how we've learned about the power of this kind of technology. But I think that the UI modes, I think the multimodal aspects of this get really interesting when you can use audio and video and numerical input and some language to as your inputs and outputs. I think that that's really where this is going to go. And in addition, I'll add to that I don't think it's going to be one model where you type into the one model and it goes out and gives you the answer. I think we're going to have many models, ensembles of models that do specific tasks. Like the model that understands lap times is not going to be the one that understands the accident prediction piece and whatever. And it's not going to be the natural language model that understands how to put that into words, right? I think we're going to have a combination of these more specified, smaller models working together in an ensemble is really how this is going to work. So the inputs are going to be multi-leveled, and the models that are trained to do these specific tasks are also going to be multi-model systems, I think.
It also sounds like a really interesting very complex computer vision problem almost as well, because you're going to have you have all these sub industries with all these different, whether it's components or pallets or packages or whatever, and the system is going to have to see what the end user is looking at or the team is looking at in a certain way in order to effectively evaluate whether whatever needs to be done in that sense. And so that's interesting. I mean, obviously it'll be trained, and so it'll get better at it, but that's also an interesting thing too, because different.
Absolutely. Computer vision is going to be a piece of the inputs here, right? One of the customer conversations we had recently was about a retail floor room in a large retail situation where they have actually cameras and data, and they're looking at customer behavior. Are you looking at this thing? Are you looking at this product? Are you touching that product? Are you interacting with that product? And then you can understand that, if we combine that with a digital twinning of that, and we start to be generative of different scenarios, we can now place our store workers to say, this person's interested in that purchase over here. You think of a car floor, and where do you send the salesperson? To the person looking at this car, person looking at that car. The one that's maybe more interactive would be the place where you want to route the attention to increase your sales. But that involves recognizing these behaviors. So computer vision can be a great input to what's happening. And there are microphones around. I know it may sound creepy, but hey, honey, look at this car over here. Do you like the blue? Do you like the blah? These kind of things could actually, both in that instant situation and also on aggregate, help for planning for retail operations in a way. So that can be really interesting. I think that the visual inputs to this are going to be really important. Same thing in a factory, not just for predictive maintenance, but for predicting buffer in a large factory or warehousing situation. Where are things supposed to be at the right times? The visual inputs to that and recognizing those dynamics are going to be a big part of the input here.
I feel like Amazon was taking there was a relatively close to where I live. There was one of those flagship Amazon Whole Food stores where they attempted to automate virtually every single aspect of the process. And when you walked into it, the entire ceiling was a grid work that was studded with cameras and microphones and everything else. And then there were sensors. You could tell. I mean, I was a little bit too inquisitive. I was like, actually trying to see like how shelving, like whether there was things underneath and so on. But they had studied the entire surface of everything with sensors and all the rest of it. It feels like, and obviously they decommissioned that, and the success rate for a lot of things, they had to hand over a lot of those processes to the humans, but that felt sort of like a first step towards a lot of what you're saying in a lot of ways, where you kind of, you have your Internet of Things, and you just kind of like stud the environment with whatever sensors and so on, and then you get all this data sluicing in that your system will analyze, and then you go from there. And I assume
absolutely. I think and this sensor intelligence is going to be a big part of the future. And you can close loop a lot of this and create a lot of optimization and therefore efficiencies in doing this. And it's good for the customer too. When you're not interested in having someone interact with you, you don't want that interaction. It's kind of a pain when somebody says, "Hey, can I help you? Can I help you? Can I help you?" And you get that 5 times. It's not always fun. But okay, when I'm really interested, I'm looking for somebody. It'd be really good if someone came and helped me. It's always there. They're never there when you want them to be. Kind of like the police sometimes, right?
It also seems like that we're potentially, as this vision rolls out, going towards a future where different sub industries and even like different facilities and stores and so on within those industries could almost have like a smaller, like almost domain specific AI of some sort. That's kind of very hyper low. Or do you think that's
absolutely? And it can be much more specified and therefore much more customized. And that's good for the company for efficiencies, but it's also good for the consumer. That you're going to get, targeted stuff. We actually don't mind in some ways giving up our privacy on the internet and whatever, because we do get better suggestions for advertisements and these kind of things, and services that get emailed to us. They're more relevant to us. There's some trade-off there, right? Between privacy on the one hand, but also getting better specified, more accurate offerings given to me, which is it saves me time at the end of the day.
Yeah, no, it really does. So I mean, in terms enterprise and industry are particularly huge. in terms of like the sub industries or the individual or the types of enterprises that are adopting a lot of these technologies faster than others, I mean, like, what do you see? Like, where's sort of the beachheads really developing in terms of sophisticated kind of maturing AI use versus industries that might be still kind of tiptoeing into it but haven't quite gone to the same extent?
Yeah, I think it is the industries that tend to have a lot of these PhD math type people internally already who recognize the value of this pretty immediately. They tend to be more of the early adopters, and so we're seeing finance is always one because you have these former physicists, PhD quant jocks who are out there and they just do math for a living for trading. So the banks. The people who do actuarial science, people who are already nerdy into the math are definitely so finance is a big area. So insurance, we've done an announcement about what we've done there in reducing times to compute things in actuarial science. Also in finance, the work we've been doing with Sumitomo Mitsui Trust Bank on trading strategies. Conditional trading strategies and using generative AI there. So finance is definitely one. Another one is pharmaceutical development. That's always been kind of math intensive, and there's a huge payout when you get it right with drug discovery, both in patient value and in financial value that comes out of it. And it is chemistry has always been mathematically pretty intense, and there's a lot of research money that goes into that. And we have a paper out there of using the quantum generative AI to develop molecules with University of Toronto and St. Jude's researchers and a company called In Silico Medicine, where we actually designed an actual chemical that works on a cancer target and knocks down that target in vitro. So this is real, and I think that so pharmaceuticals is another area. The data that you use in clinical trials is immense, and it's really important to get the statistics right there. So generating better statistical capabilities for designing a clinical trial, for example, are really important in that industry. So pharmaceuticals are another one, and healthcare is another. We're also seeing defense use is existentially important. You have 200 missiles or 200 drones shot at you. You kind of want to know where they're going, and you need to figure that out real time. And you need to generate scenarios real time with the sensor data that we've been talking about to respond to that. And those things are good in defense, but they're also important in things like emergency response. Like, what are the routes in and routes out to go rescue people in a flood, like we've had recently. So these are also important uses, and these are places where people have been using automation and AI and these kind of things at a high level because they have to do these things. So I'd say that. And then automotive manufacturing, that's another area where people are constantly trying to optimize, just in time manufacturing, just in time logistics. And the logistics industry itself is another big one.
Mm-hmm. Yeah, no, it's funny. Over the summer, I was talking to he used to be a quant, and he was saying that he was actually laughing because about there's obviously all this hype around AI at the moment, and he said that he had been on a team, I think at JP Morgan, where they've been using machine learning as far back as like the late 90s. Obviously very different than what it has evolved to at this time, but for some of these industries, it's obviously very old. So
yeah, I mean, algorithmic trading's been around for a while, and we've been using some pretty high end math algorithms to do that. I mean, that's why if you're a physicist, you can go into academia or go to banking. I mean, that's kind of like the joke. It's like, okay, I'm done with my academic thing and string theory. I think I'll go work for a bank.
No, sure. Yeah. No, I mean, or any rocket scientists, et cetera. I mean, eventually everybody it seems like they all find their ways to Wall Street one way or the other. Well, that covered a lot of ground. Here's some key takeaways from our discussion. First, AI is more than just chatbots. While generative AI has gained popularity through chatbots, its applications extend far beyond natural language processing. Zapata AI demonstrates how AI can be used to solve complex industrial problems through advanced mathematical modeling and optimization. Second, quantum-inspired algorithms can tackle complex problems. Zapata AI's approach leverages quantum-inspired algorithms to efficiently handle the complexity of industrial challenges. This showcases the potential of quantum computing concepts even before the widespread availability of quantum hardware. Third, AI can enhance human decision-making. By automating routine tasks and providing data-driven insights, AI can support human decision makers in industries such as logistics, finance, and healthcare. This can lead to improved efficiency, reduced errors, and better outcomes. Fourth, the future of AI is likely multimodal and domain-specific. As AI continues to evolve, we can expect to see more specialized AI models that combine different types of data, such as text, images, and numbers, to address specific tasks. This will enable more tailored and effective AI solutions across various industries. We hope this episode has helped you with some new insights into AI. We'll see you next time. And remember, Dice is your best resource to find the tech talent you need to fill your open roles. And for tech pros, the best place to grow your tech career.